A covalent bond consists of a pair of electrons shared by a pair of nuclei. Let's use this graph of potential energy versus the distance between the nuclei to see the change in energy as the distance decreases. We'll pay most attention to the bond in H2 and then look at Cl2 and larger halogens, defining two key bond parameters along the way. When the H atoms are far away from each other, we designate the energy as 0. As they move closer together, they attract each other more and more, and the energy decreases to a minimum. At this point, a stable hydrogen molecule is formed. If the nuclei come any closer, the energy increases rapidly as nuclear and electron repulsions take over. Now let's zoom in closer to see the overlapping atoms in more detail. When the atoms are far apart, they do not feel each other. But as they come closer, the nucleus of one atom attracts the electron cloud of the other, and the attraction draws the atoms still closer. Note the increasing electron density between them. Soon, the electron clouds interpenetrate. Attractions dominate, but repulsions between nuclei and between electrons become stronger. At the point of lowest energy, attractions just balance repulsions, and the two H atoms exist as an H2 molecule. The covalent bond is the mutual attraction between the nuclei and the electron pair. If the nuclei were to move closer, repulsions would outweigh attractions. The increase in potential energy would destabilize the system and the atoms would move apart again. In reality, the molecule vibrates, the atoms moving slightly farther and closer at the point of minimum energy. The bond length is the average distance. For H2, it is 74 picometers. The bond energy, the difference between the minimum energy and the starting point, is the energy needed to break a mole of H2 molecules into separate H atoms. For H2, it is 432 kilojoules. Now let's compare H2 with Cl2 and other halogen molecules. The much larger chlorine atoms reach the energy minimum and form a Cl2 molecule at a greater internuclear distance. Because the Cl nuclei are farther apart, it takes less energy to separate the atoms, thus a greater bond length and a smaller bond energy. Moving down group 7A, bromine is larger still, so we would expect an even greater bond length and smaller bond energy. And iodine, the largest of these halogens, continues the trend to longer, weaker bonds. Stepping back, we see that in each case, mutual attractions draw the atoms together and they form a covalent bond of specific length and energy.